Everyone. Good evening. Hope you enjoyed dinner. We're going to go ahead and get started with the icebreaker results. So basically, we're going to have the 4 finalist teams come up and give their pitch very quickly once again, and then the entire room is going to vote on the top 1 team. We know the kids won. We might be giving prizes for top 2 teams. So, first up, we have farmers.
So, Friday night, right? We're all, we're driving home. Let's just say we're a little buzz, right?
30% of deaths from car accidents are due to drunk driving, and 37% of drivers have fallen asleep at the wheel.
So we would like to propose a semi-autonomous vehicle that can detect whether you're drunk or drowsy and safely pull you over to the side of the road.
So we're going to integrate some heartbeat measurements monitor, to the steering wheel, and hopefully that will let us know if you're drunk or asleep.
And we will also be using a camera to integrate facial action unit recognition so we can know when the driver's eyes are closed.
Through this, we hope to minimize car accidents due to drunk driving and drowsiness.
And the dance one more time.
Thank you very much. That was farmers. Next up, if we could have Engineered Squad.
All right, guys, I'm Engineered Squad. I don't know where my squad is, but I guess I'm a squad of 1 now. Okay. Well, let's do it like the Army does it and lone wolf it. All right. So, first question is, how many of you guys support the military or are into some type of sports in general? Raise your hand if you are. Awesome. Well, yeah, I was prior service military. So actually one of the biggest problems that we currently have in the military is an issue with thermoregulation. So I have many friends deployed in the Kandahar province, athletes training 2-a-days in football, baseball, soccer, and they very often have heat injuries. Heat casualties are probably one of the top injuries, both on the battlefield and in actually on the football field and the soccer field, whatever. And the target of this idea is basically creating some conductive fabrics, textiles that have woven circuits to help thermoregulate your body. It plays off of an interesting engineering technique called the Pelleter effect, which basically has a plate. One side is hot, one side is cool, so it basically pushes the electrons to one side of the plate, where it's a thermoelectric cooler, if you know what that is. So you use a thermoelectric cooler integrated into a woven textile, which are out now. They're pretty common. The Special Forces use them a lot. And the woven fabric could be utilized for thermoregulation, and actually you could even integrate a circuit into it. So stroke, cardiac arrest, concussions, there's applications in cancer remediation and pre-optic hypothermia from anesthesia. So there's a lot of interesting applications for it. But it's just as simple as creating some LED microarrays in a circuit and using the Pelleter effect and weaving this into a wearable fabric like a shirt or like some pants, and you activate along the spinal cord. There's actually a peripheral controller that helps to control the hypothalamus in the brain and induce thermoregulation. It basically tricks the body into thinking that it is overheated. So it goes into thermoregulation before your body actually goes into stroke or cardiac arrest or something like that. And your glabrous skin tissues, the areas of your palms of your hands, pads of your feet, where you have very high heat transfer, heat flux. That's where you can basically, they have these large bore shunt vessels called arteriovenous anastomoses. They're basically, they're similar to capillaries, except they can vasodilate 10 times the capillary diameter. So with that, they can recruit 70% of cardiac output to these glabrous tissues to induce thermoregulation. So basically what we'd be doing is activating the spinal cord, inducing thermoregulation with this wearable technology.
Thank you to our one engine nerd. Next up, Black Dot Team.
3, 2, 1. I scream, you scream, we all scream for ice cream. We all scream for ice cream, but sometimes when you scream, your voice gets hoarse. What's a good way to quote-unquote scream for ice cream without getting a sore throat? Well, the MWT Ice Cream Delivery has found a fantastic way to do so. Using a Bluetooth-enabled app, you simply have to type in your address and your desired flavor of ice cream. Then, our employees will deliver you a fresh scoop of ice cream, as illustrated by this short skit.
I'm hungry for some ice cream. Okay, so I live here, and I guess I'll have vanilla with rainbow sprinkles. And send.
Looks like we have a notification. Well, ice cream coming up.
Wow, that was fast. Wow, that was fast.
You probably are wondering, what is that thing? Well, it is our mechanical winged cat. And that's why we're called the the MWC Ice Cream Delivery. Yes, I'm sorry. And so basically, our workers from the North Pole make the ice cream and give it to our cat, and our cat will deliver it to the customer
in 1 second. And since the wings are battery powered, you can recharge it, and it's good for the environment.
Also, the cat never has to rest. Also, you can order, if you want to, you can have a special appearance at your house.
Thank you. Wait, should I just scream? It's all free.
MWC Ice Cream Delivery! Mic drop. Mic drop.
Well, I think we all know who won the most cute award. And on to our last but not least team, underwater drones.
Man, do you guys have a really hard research question that you just can't answer?
Yeah. Bet your bottom dollar.
Yeah, me too. What are we going to do about that?
Well, one thing you can do is go on. Collab Lab. Essentially, what Collab Lab is an application that you can use to post your questions on any research question you have, and it will be answered by any user. And essentially, we have a point system in which you can spend points in order to post questions and gain points by answering them.
Yeah, and when you gain points, you can use those points to upload more questions, and it's you give some, you get some, because
Thank you very much.
All right, thank you to those 4 teams. We are going to be voting now. So if everyone could close their eyes, we're going to vote for our top 2 teams. So that means raise your hand twice for your favorite 2 teams. All right, so we're going to start with farmers. How many people will vote for farmers? Okay, and Engineered Squad? Okay. Black Dot Team? All right, and finally, Underwater Drones. Yes, this is Collab Lab. Okay, you guys can open your eyes. So in first place, we have the Black Dot team. So for all of them, we have IEEE Connecting Brilliant Minds t-shirts. You guys want to come up and get them? Perfect.
So 2 more or maybe I'll give them cash.
Okay. And in second place, we have farmers, and each of them gets a $20 Amazon gift card. If farmers could come up and get their award. All right, on to some other awards. We gave an award for the best team selfie. So we originally only planned to choose 1, but there were 2 that we found it really hard to break the tie. So that's why we have 2 teams. Team Blue-Green for their MIT, and Team Legendary for taking a picture with a dairy cow. And for these teams, we have IEEE t-shirts and umbrellas. And come down for your awards. Okay, so at this point, we're going to get a little bit more serious, and Soon-Won is going to present the Best Paper Award.
All right, good evening. That was the best ice cream breaker event I ever seen before. I hope you guys all enjoy. So those are kids, right? Actually blow my mind, right? Okay, congratulations for those who actually win the prizes. So let me present the Best Paper Award. So I want to briefly go through the process, how this best paper being determined. So the study committee actually nominated the top 6 paper. They feel that they are eligible to win the best paper award. So these are the 6 nominated paper. Hopefully you recognize one of them, all right? So then I stripped down the school and the name, the author name from the paper. Then I forward all these 6 papers to the IEEE Boston Section Executive Committee. So have them to judge the best paper award. So what they did is that, so they received all these 6 papers. By the way, on that executive committee, they're all mostly are retired, and mostly they are for industrial professionals. All right? So they may have different expertise in different technical field, but they all review all these 6 papers. So what they did, first round, they came out the top 3 paper. Right? I'm sorry for those who really, okay. So these are the top 3. The executive committee came that they should win the top paper. Right? So then the final round, so the executive committee will have to rank them. So which one is the best paper, the second place, and the third place? So you guys all ready? You guys don't have paper, right? All right, hopefully when you guys grow up like that, submit paper to me, okay? The third place go to the dry field filter design for magnetic particle imaging application. Is the author here? Come on. We have a certificate for you. No? So how should we pick another one? All right. All right, the second place go to an indoor precision system facilitated by computer vision. The thermal energy harvesting for cell-powered smart home sensor. Good job. Congratulations.
All right, congratulations to all of those paper authors. And keep in mind that we are still having votes for best paper presentation and best poster. So even if you didn't win best paper award, you could still get something. And at this point, I'm going to introduce our next speaker, Dr. George Yakos. He is a professor and chair of the Department of Electrical and Computer Engineering at Manhattan College. He is an IEEE Fellows and very closely associated with the IEEE organization. So without further ado, we're going to welcome him. And also, just to let you guys know, we will be handing out certificates to all of the paper presenters at the end of the speech. So thank you, and make sure you don't leave without those.
Good evening to everybody. My name is George Yakos. I'm going to present a work on drones, on how to improve the performance of drones using biomimetic systems. First of all, I would like to thank the student committee, the organizing committee that invited me to give this talk here. Over years, I serve as a mentor to students First, we're trying to get our degree. Then we have the tenure process. At the same time, we're supervising students. We're mentors. After years and years, we understand that also students serve as mentors to us. In the aspect that students can motivate us, can give suggestions to us, can, with their enthusiasm, they give message that we have to outperform, we must do better job to meet their expectations. So this is our primary goal, and this comes after years of being in academia, that we don't only serve as mentors, the faculty to the students, but also the students to us. This is my experience. And one valuable lesson is that I'm looking from the students the teamwork. Teamwork. This is very impressive, and this is a motivating, a driving force for us to imitate what job are you doing here, what job did this committee, this student committee. Now, talking about the topic here, we have the agility. What is missing from drones? Agility. This is the key factor. Drones is a technology like aviation, is man-made technology. We're trying now to pass some bio-inspired principles into the design of such systems with respect to the vision and other parameters. How successful we are, I will tell you the problem is very complex from the beginning. The problem is complex because there are several factors involved to this. Here is the definition of the drones that you have here. Let me see this. Does works this? Oh. We have three categories of drones: ground vehicles, unmanned, underwater, and unmanned aerial vehicles. Both are equally important. Applications in defense and civilian applications. So there is an array of applications for defense mostly. And now we start also in the civilian sector: agriculture, mining, forensics, inspection of bridges, tunnels, and other structures, underwater inspection, perimeter security, and so on. You see the global aerial drone market. The military dominates for a number of years, but also the civilian starts to pick up, you know. How is going the market in terms of different continents that we have? We see the United States is number one, followed by other continents: Asia, Europe, Latin America, and Middle East. There are some limiting factors of drones. These regulations and safety concerns, which they limit the dissemination of drones to commercial sectors. In general, there is room for the development of drones. The military sector is going to lead. However, we have potential commercial applications, but enterprise applications are going to outperform other commercial applications. Technical challenges. Ability of drones to operate in an urban, crowded environment. There is a big problem because they lack agility. They lack agility, plus their design requirements, they are competing with to each other to develop a system with scalability and agility. Specifically, We have limited capabilities to operate in confined, obstacle-cluttered environments of city streets, close to terrain structures, or to vehicles to be able to jump from one car to another. Autonomy, a limited understanding of low speed. More challenges. The multifunctional sensor architecture, the guidance ability, the flight is confined in airspace, you lack ability to have high peripheral view, so to be able to react with situational awareness when needed. And many biological disciplines cannot be described by mathematical formulas. Why? Because we have also psychophysical parameters that compound the movement of the animals, insects, as well as vision, affecting the vision, which our humans, we don't have these capabilities. Now, if you ask me the question, which has better vision, the humans or the insects and the animals, certainly I will tell you the humans has better vision. Simply we're trying to get we're trying to get positives from the insects and animals that we can apply to the design of the drones. You know, the evolution about the vision happens 500,000 years before. So 500,000 years ago started the revolution before people, I mean animals, was working, was taking vision, not images, but intensities, like a pinhole camera. Over years, because of the predator animals, they developed autonomous vision, and we have these several vision systems. Some appear incomplete, some they have positives with respect to the human vision, but still the human vision is considered the best vision overall. We have more challenges. The guidance systems rely on few high-frequency sensors. We have central digital data processing. We don't have decentralized, we don't have distributed system of sensors like the animals, antennas. The animals over their body, over their wings, they carry antennas, they have sensors. Distributed motion, we don't have this, everything centralized. Model-based algorithm designs, I apply this. High-speed digital microprocessors, which implies what? Implies high consumption of power, large number of data, which is against the design of a drone. Okay, so these are negative issues. And we have another problem is the relative tight tolerance on sensors, processing, and accessor systems. Miniaturization of the visual system. This is a big problem. Try to make a system, the visual system, miniaturized as of an insect one, you limit the image quality. The image quality deteriorates because you have to put let's say, in 4 centimeters, you have to put everything together, and this creates significant stress to the image quality, contrast resolution, spatial resolution, everything. And similar, we have limitations of the underwater drone systems, poor visibility, low contrast, blur imaging. Most of the problem is in underwater systems, we have variable illumination, and this is one of the toughest problems in imaging is to solve problems under variable illumination. So this can be a problem. And now we have here can biology impact man-made designs? This is the question. Well, they excel, certain insects and animals excel in controls in terms of agility and robustness. So somebody can say that we have to adapt insect-animal vision models combined with artificial intelligence. Okay, bio-inspired vision. There are several advantages and several disadvantages. Let's talk about the advantages. We have, in terms of flying physics, different type of wing kinematics. They are good to avoid obstacles. Compound ties, which they provide several functions different than the human one. And we have drawbacks. We have negatives. They can detect fast movement. They can detect polarized light. We can detect only intensity and color, nothing else. So they can provide attitude reference information essential to level flight and homing behaviors. They have the ability to go to their nest, not only by using a compass like the skylight, polarized light from the atmosphere, from the sky, but also they use homing. Homing is, what does it mean? They look at salient features, at distinct characteristics, and based on these few points, they are able to make a reconstruction of the scene. And this is, I'm telling you, one of the ways that today the systems are being designed. They're trying to apply, to use salient features in order to utilize, trying to get the global picture, utilizing few elements, and this brings down the computational speed. This brings down the power. So, however, we cannot relate the biological processing with engineering design principles, are not compatible. Biological systems possess sensing, computational, accessory responses architecture, which differ from the engineering that we are using today. Indeed, exhibit psychophysical behaviors which affect the vision, the movement, or vision combines to the movements combined to the vision. Everything together with the psychology affects their vision systems. Those differences are poorly understood. The miniaturization is a key issue of degradation of the image quality. If you are going to put in a very limited space all the objects, you have limited focal length, you have limited few pixels. Therefore, this is going to affect the bandwidth capacity of your system. This is the compound eye. The compound eye is this. You have two different architectures. This is the human eye. You see the compound eye. 1, 2. You have elements here where light, several pixels are intercepted. You see this is peripheral view is extended. So what does it mean? They can see movements here and there without rotating the head like that. They can see from here, okay? The compound eye, on the other hand, the imaging converges at one point, so you have better intensity here. And this is the human eye. So it's here, you see this system allows to detect very fast movements because of the architecture here, several elements, one next to the other. Can you tell me what can be the disadvantage of this geometry? What can be the disadvantage of this geometry? It has advantages and disadvantages.
Collision detection.
Sorry?
Collision detection. If you could track very quickly.
Correct. No, the disadvantages. Correct.
Disadvantages.
One is
Poor focus.
Eh?
Poor focus.
Poor focus, yes. One. Excellent. You don't have focus, actually. Number 2.
Bubble vision.
Blurry vision, yes. You say the same thing. Blurry vision.
I said bubble.
Bubble vision. Okay. secondly, there is diffraction limit. Due to diffraction limits, you know, that we have here makes blurring the vision, you know, plus the lack of focus. So this eye here, I will show you some simulations that I did, bring some negative issues. We're looking to the positives. We don't look into the negatives. So this is typical. This is the complete eye. You see, you have here, you have one system design parameters here, one aperture. We have here a second aperture we have here. Okay, this is the ommatidium. This is the rhabdom. So in order to calculate the modulation transfer function of the system sensitivity, you must consider both apertures, both this aperture and the other aperture. So all these equations, the design parameters, they compound into some equations. The equations are the sensitivity, which combines both parameters, angular sensitivity, and you come to the modulation transfer function, which expresses the contrast versus the frequency. Now, this is the formula for the MTF, okay, which is typically, say, Gaussian, you know, which you're using the angular sensitivity here, you know, so you make this plot. I omitted one slide here, the implementation design. If you go to the reality to design an eye, biomimetic eye, you run into problems with the semiconductor know-how. I mean, you get problems typically with the innate plant structures that we have an ability to design curves in semiconductor technology. So one problem is how we're going to make this curve structure to increase the peripheral view. And there are other design parameters. Although semiconductor industry is mature for microchips, this technology lacks the maturity. This is the problem. We discussed about this. Now, some simulations I will show you. Some simulations we see here. I took the laser beam from our lab and we created the footprint for certain distances. This is the footprint of our laser beam and how it's going to be intercepted by an insect. An insect, how it's going to see, to perceive this. You see, we have different insects with different angular sensitivity, and we see how it's perceived at 1 meter, distance 5 meters, 10 meters. And now there is some blurring, which I cannot see it, and I say, okay, I'm going to, instead of using the bar pattern, I'm going to use the US Air Force bar pattern so I can see clearly spatial and contrast resolution. So the same insects, they're going to see obviously blurring, you know, at 1 meter, at 5 meters, at 10 meters. Detection characteristics of the insect eyes is wide angle vision, agility, polarization capabilities, which are unique. However, they have, as we say, homing, key point detection. However, they have poor light reception, poor collection efficiency because of the small size of the element. Mediocre spatial resolution and blurring. These are the negatives. The polarization sensitivity is very important because you can use to detect several applications, navigations, camouflage breaking, intraspectral communication, contrast enhancement. Besides that, I'm using the lab polarization to bypass its very strong pre-processing technique. You don't have to to apply smoothing filters. Sometimes it bypasses also the segmentation because by using stocks parameter images, you can bypass the segmentation process. You can go directly to the processing part, feature extraction, and so on. So it's a very flexible tool. And here you see the skylight is the ability of the insects to see the polarized light. And this serves as a compass to them. You see now here you have, besides that, you have different antennas and different chemoreceptors which distributed all over their body, which have the ability to get local, to detect local effects. Okay, everything we're going from the global imaging and sensing to the local imaging and sensing. This is the trend from the next years. You see here how starts this phenomenon. Several insects, they have different abilities. Some people, some animals detect UV, polarized UV. Others detect, they have blue receptors, like the crickets. You know how it happens, the light is, the sunlight is unpolarized, interferes with the atmosphere, and through Rayleigh scattering, which is proportional to the inverse of the fourth power of lambda. That means blue light is visible instead of red. You have the scattering here mechanism. You scatter it, change polarization, becomes partially polarized from unpolarized. Part of the light, however, will be incident on the sea surface, where it becomes reflected, and this introduces partial polarization. Again, they combine here, you have this, and here everything compounds to a figure of merit, degree of polarization and the direction of polarization. This is the elementary explanation, and how you can see why insects can see polarized light. Going now, I'm going to show you an experiment which highlights the potential of the polarization that the animals can see. Here you see a translucent bar pattern, this line with nickel deposited on it, and there is sandpaper behind. It is illuminated. The sandpaper is different gauges, different knots. You illuminate by a polychromatic light, and you get a scattered radiation back here. You are using polarizer in the transmitter and polarizer in the receiver. This is the physical size of the physical composition of the paper, of the sandpaper. This is the geometry that you use here. This is polychromatic source. This is the receiver with the camera. And here what you see the unpolarized images, the A0. The A0 is all the light, polarized and unpolarized, at different grids, high roughness with progressively diminishing roughness. You go here to 400 grids, which is almost specular, like specular reflection. You see how looks the pixel? No polarization here. Now, you do the same experiment under using polarization, and you see immediately you have an improvement of the acquired images. These are the DLP images, okay? This is at high roughness, progressively to low roughness. You see an improvement, and somebody wants to know more, wants to know about the noise. Okay, you apply a standard deviation filter, a DOP, and you get here, you calculate the standard deviation on each pixel, and what you find here, you find now the noise associated with the scattering, okay? Noise associated with the scattering means that here you have a lot of scattering because you have a high roughness, material roughness. Progressively the noise, the scattering radiation decreases. So this gives you information. You can relate this to the DOP. This answers the question of Joe, my student. So going downstairs here, polarization is one factor of the insects that you can take into account. The second is the key point detection. So we are looking for specific salient features. So important is to define a multi-scale mechanism and then apply recognition, localization, and other artificial intelligence algorithms. Now, example, I'm going to show you another example. Extract and depict 1, 2D elements, 1D signal, just one from a point detector, into higher dimension images. This is part of the polarimetric fractal analysis of space materials, which was a 4-year contract. And this is the results. You see what you do. You take one point sensor, you get this kind of signals under different polarization geometries. Okay, these are harmonic signals, time series. And here you get their scalograms. In this case, we have from the one material here, this is amorphous silicon, and this material here is polysilicon. This has enhanced specular characteristics like mirror. This diffuses more, and you see the difference here. I can see here the physical characterization. I can get physical information directly from this signal. And I can see that here there is associated more of diffuse scattering here. Here the diffuse scattering is reduced. Here is the cross-polarized geometry. Cross-polarized geometry, where you see it's more pronounced in the higher scattered medium, that's polysilicon. As I say, this is amorphous silicon, this is polysilicon. I have a two-dimensional, actually more than 2 dimensions visualization of 1D signal. And this means, to me, means a lot. It means that I can get salient features, few points, and I can get complete information about the target without need to use GPUs, to use graphics processors, because I bypass them. I don't need them. I need only few elements to make reconstruction of the target, of the cell. This contains a lot of physics, a lot of physics. Physics without engineering cannot be done, you know. So the big picture now here, we have several of them, and after you can do pattern recognition, you can apply any technique here to make feature extraction, okay? You have different scalograms. Similarly, polarization can increase the underwater images because they tend to be preferred light polarized in the horizontal direction, so we can remove the unpolarized light, the scattered light, and this is very important. One of the techniques, you have several techniques for underwater images, you have confocal microscopy, you have several techniques. One of these techniques we are talking specifically. Possible applications of the biometric vision applies not only to drones, to different areas, robot orientation and navigation, automatic target detection and recognition, big science and technology in this area here. And scene segmentation, you can bypass the segmentation if you're designing a good polarization experiment. You bypass the filtering, you bypass the segmentation, you go directly to the processing because polarization is the pre-processing of the image. Scene segmentation, camouflage breaking, communication, and underwater vision in design of medical imaging devices like this that was presented by my students in lung cancer detection. Again, detects, again, the relies on polarization of light. And you see now, coming to the conclusion, we have some technical challenges, actually a lot of technical challenges associated with the limited agility and vision capabilities of the drones, which were introduced. Advantages and limitations of using biomimetic behaviors were discussed. Finally, examples highlighting the potential of polarimetric detection and key points detection were presented within the time content that we have. And here, I use the reference. I have a series of reference here. And here we have the, thank you very much, and a big thanks to the students who contributed to this project. Thank you very much.
Thank you so much to Dr. Yakos for coming to talk to us tonight. So this concludes our evening session. So we will see you all tomorrow morning. And again, reminder to paper presenters to pick up your certificates before you leave. Thank you.